Hi guys. Well, this is chapter 12, final chapter, and this is on correlation and regression. As per the previous chapter, the book does kind of a lot of things, but doesn't do any of them very well. So I've tried to focus in on a few of the core concepts. We're going to cover in particularly correlation and simple regression. Again, just watch these videos and also pay particular attention to the revision guide because that will give you kind of lots of examples of the sort of questions that I can and might ask in the exam. And just another thing, we're going to cover three topics. We're going to cover correlation, we're going to cover simple regression, and we're going to cover multiple variable regression. I'm not going to include questions on multiple variable regression in the exam. The exam is purely going to be correlation and simple regression. But when you're building models, you're doing some analysis for your actual project, multiple regression is actually pretty important. Okay, so we're going to start off with this kind of idea of correlation. Now, correlation, and I'm going to show you some examples of correlations in a minute. Correlation is just telling you how related two variables are. So if the time you study for an exam versus your score in the exam, you would hope that those two things would actually be positively correlated. So what we're going to be doing over the next few slides is we're going to kind of define things like positive correlation, negative correlation, and we're also going to talk about relationships where it's not linear, where there may be a curve in the relationship. Okay, so let's start off and let's give a few examples of each of these types of correlation. So I'm going to kind of annotate some of these kind of correlations here. Just let me get my pen. So this is an example of a positive correlation. As x goes up, y also goes up. So let's think of a few examples. So maybe I have as my temperature goes up, then ice cream sales should go up. Yeah, the two should go up together. And it's not going to be perfect. You might have a day with high temperature and not great ice cream sales because in the real world, these things are never exactly perfect. Now let's think of a country of different countries. So each of these dots would be an actual country. Let's just have the GDP per capita versus the proportion of people in higher education. And I'll just call it HE. I.e., as countries become richer, you will generally get the idea that more people would actually become, wouldn't finish at school. They would actually go into higher education. And let's just have a fun one. Imagine you drink more. Yeah. Sorry. Okay. Let's just try that again. Imagine you drink more. So we'll have alcohol consumption versus reaction time. As you consume more alcohol, your reaction times would probably become much slower. So that's why you're not supposed to drink and drive. You have very slow your kind of response times get much bigger as you consume much more alcohol. So, as you say, drink 10 pints of beer, you might kind of take you 10 seconds to respond to something that would only take you maybe 2 or 3 seconds if you hadn't drink 10 pints of beer. Okay, so let's have a look at negative correlation. So here, as my x goes up, my y goes down. So it's going kind of in the opposite direction. So let's just kind of think about this. So maybe time exercising versus weight. That would be a good example of something that should be negatively correlated. As your time goes up, as you spend more time exercising, your weight should go down. Another thing, maybe temperature, to give an even example, versus coat sales. So as my time, as temperature gets higher, we're going to sell less coats. So that's kind of an opposite example. And let's just have a matching example. We'll have GDP per capita versus infant mortality. Again, as you get richer, your level of infant mortality tends to go down. Now let's look at zero correlation. These are things that possibly should not be correlated at all. So think the things that are kind of, completely and utterly unrelated. So let's just have the temperature versus, and let's just think something that's unrelated, reaction time. Your reaction time does not change with temperature. Hopefully not. Unless it's incredibly, incredibly hot. So these are things where there's kind of little or no correlation. The X and the Y are almost random. There's no correlation. Now, perfect correlation, we don't have to really worry about this because this does not actually happen in real life. But, a variable with itself. So if I correlate temperature and temperature, and maybe something, we'd still have perfect correlation. We'd maybe have a weight of somebody in pounds versus the weight in kilograms. But these perfect correlations don't occur ever in real life, ever in kind of any business scenario. So the last one, this is kind of the curvilinear. This is told in the last slide. As X goes up, Y goes up. And then it comes back down again. So let's just have a look. Maybe price on the X. If you guys, I'm sure you've all done the intro economics course. You've seen these sort of curves. And versus profit. So you start off with a low price and the price is less than it costs you to produce. You don't make a profit. But as the price gets up, your profit increases. But you get to a stage where you're selling it for too much and people don't want to buy your product. So your profit goes down. Price versus profit. And let's just say, let's have a silly one to finish off. Let's just do alcohol. I will say beer drunk versus your darts performance. Now, when I was a little kid on TV, they always had like the World Darts Championships. And the people playing the darts, they weren't exactly athletes. They were all like huge guys with like big, big pot bellies. and they always used to drink beer while they were playing darts. And this was like the world championship for the sport. And eventually, this was banned for being bad, bad public health publicity. But I think the idea is that having a little bit of alcohol kind of steadies your hand, but as you have too much, it begins to affect your coordination and response times. So there's like a peak amount of alcohol drunk for playing darts. At least that's kind of the theory. So that was a bit of a silly example, but again, it's an example of a curvilinear relationship. So let's go to the next kind of thing. So basically, when we have correlation, we're measuring with a normalized measure of what we call covariation. So the change in one variable related to another. And what we've just been showing is something called a scatter diagram. So let's just kind of have what I've just done. These guys are all scatter diagrams. Okay, so here's another little example for you. Here we have basically a business example. And as we kind of go up, we have the packets of items that we've sold. Maybe this is detergent. And relative, this is kind of the number of adverts. And here, this is kind of a positive relationship, but it's not like an incredibly 100% positive relationship. Now, this is what we did. When I was business stats, this was kind of horrible. I made people actually calculate this because I was a horrible person when I taught stats. You don't have to calculate correlation coefficients from hand. You just need to know that a perfect positive correlation is 1, a perfect negative correlation is -1, and no correlation, kind of that cloud structure, was going to be 0. So let's actually have more examples. And I put together a little bit of spreadsheet. I'll put this online. So this is kind of my advertising versus sales of packets example. I've put it in Excel. And all those horrible equations, I've basically put into Excel. You don't need to know the equations, but again, it's just a little bit more intuition here. So here we have an example, which is a positive correlation. So you see, as my advertising revenue goes up, my sales increase, but it's not completely linear. We have examples where we have advertising revenue of $1,000 and $2,000, and we sold 1 packet, $3,000 and $4,000, and we sold 2. I guess to make it worth your while, this should be a high volume product. This is in thousands, and we have $5,000 advertising revenue, and we're making $4,000 in sales. So this is not a perfect correlation. The correlation here is 0.9. So it's highly positive, but it's not exactly perfect. Here's a perfect example. So we sell 1,000, we make 1,000 in sales. Have 2,000 advertising, we have 2,000 in sales, etc. This is a perfect correlation. And you can see here the correlation is going to be 1. Here we have a little bit of a shift. For $1,000 in advertising, we make 3,000 in sales. For 2,000 in advertising, we make 4,000 in sales. And you can see we can plot these here in a straight line. Again, it's still this straight line. There is no error. So even though it's shifted, we still get a correlation of absolutely 1. And then here's another example. This is kind of multiplied. So here we have advertising of 1,000, sales of 5,000, advertising of 2, sales of 10. But again, there's no error. We have this perfect relationship here. And with this perfect relationship, we have a perfect correlation. And here we have a constant. And in fact, there's no correlation defined for this. Here we go. Basically, maybe we just got a really incompetent advertising staff. So no matter how much we advertise, we always get exactly the same scale. And the idea is there is actually no correlation for this. This is undefined. So here we have a negative example. And we've got an incredibly incompetent advertising department now. And so if we have 1,000 in advertising, we have 5,000 in sales. 2,000 in advertising, we have 4,000 in sales, etc. So there's this perfect negative correlation. And here, the correlation is -1. And here's a little example. I'm going to talk about this example later when we do regression. So here we have a measure of social media buzz. This is the tweet rate per hour of a movie in the week before its release versus the revenue of the movie. And again, we've got our correlation is about 0.9. So there is this relationship here. As the movie gets more social buzz, it's more likely to be successful at the box office. Okay, so let's kind of go back to the slides. And so this is what we talked about before. The correlation varies, the standard Pearson correlation, the one we're going to talk about in class, varies between -1 and 1. 1 is this absolutely perfect positive relationship with no error. And I'm glad I've shown it you in Excel because I very much doubt I could draw a perfectly straight line. But this is a correlation of 1. And that's a correlation of, and you have to use your imagination. Imagine I was a good artist and this was like a perfect negative correlation. And again, so that looks like it's been a power of something, r equals -1. And then we have like this absolutely no, we have high and high y for high x, high y for low x, low y for high x, etc. There's no real pattern here. Then we have a correlation of 0. Now, just to give you an idea, we'll discard that. There's a little, this is kind of quite funny. There's a little game here where it actually shows you correlations and you've got to guess the correlation. So remember, perfectly positive is 1, perfectly negative is -1. So let me guess this. This looks like a moderate correlation. I'm going to say 0.5. And I got close enough. This is a reasonably positive correlation. I'm going to say 0.75. And this looks pretty strong. So I'm going to guess 0.9. And yeah, I was really close. I got a little bit of a bell. And this looks still relatively close. I'm going to say 0.89. Now, maybe I was thinking of actually challenging you guys to this, but it's probably difficult in an off-classroom setting. So when it comes, just as an aside, when it comes to the exam, I may show you some of these, but it won't be subtle. It won't be like, is this a correlation of 0.8, 0.9, 0.85? It would be like, is this a correlation of 1, -1, 0.5, -0.5? So you need to know, what's perfect, what's not perfect, what's negative, and was positive. So here we did the correlation. Here's some kind of rules of thumb of how strong the relationship is. So 0.8 and above is very strong. 0.6 to 0.8 is strong. Then we have moderate, weak, and no relationship. Now let's just think about some of the assumptions here of the correlation. Now, the correlation we're using is called the Pearson correlation. So this is the assumptions for the Pearson correlation. The variables should be interval or ratio scaled, i.e. they should be continuous. And to measure the Pearson correlation, we're really measuring a linear correlation. So if we have this sort of instance, our Pearson correlation is meaningful. But if we've got the curvilinear, which I showed you before, then you can still calculate a Pearson correlation, but it would try and fit this line and would say, hey, this is a really bad relationship, but in fact you do have a really strong relationship. It's just on a curve. So it really needs to be straight line. And the variables, now just to note here, I've put in brackets, this was from the book, but I put something in brackets. The variables to be analyzed have a normally distributed population. You can calculate a correlation coefficient with any distribution of variable. For some of the statistical tests that we're going to be kind of covering in the covering in a minute when we do it in SPSS, you actually need to have normally distributed populations, or maybe at least a big enough sample size so the central limit theorem kicks in and you assume your data are normal. Again, don't worry when you're doing your analysis of projects. Don't just worry too much about this. Just assume that your kind of variables are good enough so you can calculate correlations. People rarely pay a lot of heed to that. Okay, so I want to show you one more thing, and it's just a little aside. Just because two variables are kind of correlated to each other doesn't mean that one causes another. Typically, to prove something is one thing causes another thing, you really have to have an experimental setting where you're properly controlling your variables. So just here's like some interesting things where things are actually highly correlated. The gray here is really bad. So I'll read this out. This has the correlation. So I'll read this out to you. So this is the divorce rate in Maine and the per capita consumption of margarine. And these things have a correlation of 99%. Or 0.99. So they have really high R. They kind of go down together pretty much. And I think it's just two things that are slowly going down over time. They're not, one doesn't cause the other. And here we are, the per capita. This is curvilinear, so it doesn't have a great correlation. It's actually a correlation about 0.9. Per capita in consumption of chicken and total US crude oil imports. Again, it's almost just a chance thing that these have come up and down together. And per capita consumption of sour cream and motorcycle accidents killed. Number of people who died becoming tangled in their bed sheets and total revenue. And in this case, this could just be actually, because this is raw, this just might be a function of the US population going up. US crude imports from Norway and drivers killed with railway trains. So we just had a spike in 2002 randomly for each of these, and they're both going down. Per capita consumption of mozzarella cheese and civil engineering doctorates. Maybe, you know, mozzarella is becoming more of a trend, and civil engineering is becoming a more important topic, but one's not related to another. Here's just a silly one, correlation of 0.67. Age of Miss America and murder by steam, hot vapors, and hot things. And again, this is probably related to the overall population. You can actually account for the overall population with things called partial correlations, but that's a little bit beyond this course. But we've got US spending on science, space, and technology, and the number of suicides by certain methods. And finally, I'm going to give up here because it's getting very silly. Number of people who drown falling into the swimming pool, and number of films Nicolas Cage appeared into. And that's 0.67. And I think this is just a case of, you know, this is what we call sometimes data mining when we abuse it. We have thousands and thousands of variables. A few of them probably randomly correlate. And we found two that randomly correlate. But the two are probably very definitely not actually related in any way, shape, or form. Okay, so we'll just kind of stop there for a minute. And then we will go to looking at correlation in SPSS and some of the statistical tests that you can actually do